All right, the recorder is on, so I have to be careful of what I say. I'm always careful. Hmm? Oh, all right. This is the wrong class. I have to kind of switch over to this class.
Is that 430?
This this is 310.
310? Okay, because in 430, we're doing push pop stacks for C++ coding.
Mm-hmm. Yep. But it's also the stack structure is also useful in many other classes,
Yeah.
and that's why I have to talk about the stack in CISP 310 because that's what calling and returning is about.
Mhm.
The last function that you call would be the first one to return. I mean, that it just kind of makes sense. But that's also last in, first out,
Yeah, like
which is what stack is about. Yep. Okay. All right. So with this class, we are pretty much done with discrete probability. I think for this semester, I will give you a sample of the final exam from previous semesters. So that would give you guys a longer period of time to kind of get used to the kind of question and also to give you more time to think about a strategy of how to solve those problems. And I will explain that to you as well. But I think it just takes a little bit more time to really kind of process all of that stuff. So I think that's what I will do. Um, so we are now in the graph stuff, and we are going to talk about the A star algorithm as opposed to Dijkstra's algorithm in today's lecture. But before I start with, let me go there first, and then we'll kind of, and then I'll ask some questions. All right. So are there any questions about Dijkstra's algorithm? Are there any questions about how I traced or hand traced Dijkstra's algorithm in the previous class? No questions? It's all good? Kind of makes sense? Okay. All right. So with that said and done, and I'm double checking to make sure the recording is on and it's all recording correctly, we are now going to get started with the A star algorithm. I really have no idea why it is called the A star algorithm. It also has some companions like C star. It's kind of interesting, because there are variations of the A star algorithm for kind of like specialized applications. All right, so I'm going to read this kind of sentence by sentence, and then we'll see whether there are questions or not. So the first thing is it differs from Dijkstra's algorithm in the sense that it makes use of a heuristic function to guide the search of the shortest path. Last time on Monday, I gave you guys an example, right? We are using a map, finding the shortest path with a navigation system, using that as an example. So the heuristic function is typically something that's very easy to compute. It will give you an estimate of the actual shortest path between two vertices, but it will also make sure that particular estimate is not going to overestimate. It can underestimate, not a problem. It can be exact, which means, why would you even need an algorithm, to begin with? But it just cannot overestimate. Okay? So that's one restriction of the heuristic function is it cannot overestimate. So it would be nice if it is quick to compute because it is something that we're going to have to call very frequently. And it is the intention of the heuristic function is an estimate of the actual shortest distance between two vertices. So it doesn't have to be accurate. Okay, if you say, well, I can do this, but it's not going to be very accurate, it's fine, not a problem. The only question is it always going not to overestimate? That is the key issue, is we do not want anything that potentially overestimate the actual shortest distance. The A star algorithm can only handle one single destination. I'll call that X, within this particular discussion. So the heuristic function really only need to be this, okay? It only needs to map to, we only need the heuristic function to be defined when we are looking for the pair of any vertex to the destination vertex. So that gives us, the pair of vertices and it maps to a non-negative real number. Okay, so I'm just going to pause here and see if there are any questions about the notation of h, which is representing the heuristic function. So we are good with the h representation? We good? Okay, all right. So once I give you an example, it'll be kind of clear. Um, all right, so we have, in order for the A star algorithm to function, the heuristic function has to be quote unquote admissible. Admissible simply means that it cannot overestimate. That's the only, it's just a term to say that it cannot overestimate. So technically speaking, this means that if L of x v Cartesian product if with v maps to non-negative real number represents the actual length of the shortest path, then the heuristic function has to be less than or equal to the L function. So that's just a more formal way to mathematically express what I said verbally. Are we doing okay so far with the terminology so far introduced? Okay, all right. So typically, the heuristic function is likely to be underestimating, but occasionally you might have a heuristic function that occasionally will give you the exact value of the length of the shortest path between two vertices. That doesn't happen very often. So note that one way to define the heuristic function is just to say, everything is a zero. So in that case, we are degenerating the A star algorithm to behave like Dijkstra's algorithm. Okay, so kind of makes sense, right? Because without the guidance of the heuristic function, it just expands, on in a concentric way. It starts with the origin vertex, where we start, and it keeps expanding until we get to the destination vertex, which is basically what Dijkstra's algorithm would do, because it is not guided. All right. So in my case, okay, this does not apply to CISP430. While Dijkstra's algorithm explores backward from destination vertices, the A star algorithm explores forward from a start vertex. The following represents the pseudocode of the A star algorithm. So are we okay up to this point? The main point is, do we understand what is a heuristic function? What it is representing? All right, cool. So now we actually dig into the algorithm. They're all basically, these are the givens. All the let something is a given. The first one is easy. The graph in question is represented as a two tuple. V is a set of all the vertices, and then Y is a set of all the edges. Okay, no big deal, kind of the same as Dijkstra's algorithm. The second one is also kind of the same as Dijkstra's algorithm because we have a function D that maps each edge to a non-negative distance value. So that's also kind of the same as Dijkstra's algorithm. The third one is a slight change, um, because in Dijkstra's algorithm, at least the one that I talked about in this class, there's no such thing as a start vertex because it finds the shortest path between every single vertex and a destination vertex. But in the original Dijkstra's algorithm, it might have a start vertex. So let me ask this question. Has Iraj started to talk about Dijkstra's algorithm in 430? Is he planning to? Is it in the... He's planning to? It's kind of late. Okay, so, um, all right.
Some kids were making fun of him for that in our last class.
Sorry?
Some kids were making fun of him for that in our last class because he's a little bit behind.
Okay. Alrighty. Okay, so in A star, we do have to designate the start vertex. In other words, where are we at this point? And then we use a different vertex, which is x here, to designate the destination vertex. So are we good so far? So all of these have to be given in order for the A star algorithm to function. You have to tell me What is the graph? Okay, what are the vertices? You have to give me all the edges. How are these vertices connected? You have to tell me the distance function. How much does it cost to go to traverse this particular edge? You have to tell me where we start. You have to tell me where we are supposed to go to. And then there's one more thing, which is the heuristic function. So the heuristic function, as discussed earlier, in this form, it is more generalized, but it doesn't have to be this general because we know that we only need to find the heuristic function from a particular vertex to the destination. So this v here can be substituted with just x and would just be fine. Is that okay? All right. So now here's the actual algorithm. You can see that the actual algorithm seems to be, oh, wait, nope, this is not it. This is also initialization. So the initialization is to say for each vertex v lowercase in v uppercase, do the initialization. If v is not the start vertex, then we perform these particular operations, and only for the start vertex we perform these operations. So this time, instead of the L function, we have G and H. Um, so the easy part is to mechanically just explain for anything that is not the start vertex, G of V as well as F of V are initialized to infinity. Okay, that's pretty easy to explain. That's just mechanical. The question is, what are they representing? I think that is more important because we need to understand what G of V is representing, also what F of V is representing in order to understand the algorithm. So the explanation is also included here. G of V is the actual length of the shortest path currently known from vertex S, which is our start vertex, to vertex V. Is that part okay? In some way, it is kind of like the L function, except this is this is the length of the currently known. Okay, let me rephrase that. This is the length of the currently known shortest path from the start vertex to the vertex that is serving as the argument of the g function. We doing okay so far? Does that explain why g of v is initialized to infinity for anything that is not the start vertex, and also why for the start vertex, g of v is initialized to 0? Because for the else case here, g of v, v is actually the start vertex already. So I'm really asking, what is the length of the currently known shortest path from the start vertex, there's only one, to the start vertex? You go like, that's a stupid question to ask because we are already here, we are already at the start vertex. Of course it is 0. The length of the shortest path from the vertex to itself is going to be 0. We are already there. So that kind of explains why it is initialized to 0 for g of s, but for any other vertex, it's initialized to infinity because we are making that grim assumption that, well, maybe we can't even get there. Maybe there's not a sequence of edges that will lead me from the start vertex to that vertex. So we just go like, well, assuming until I see the path, I'm going to assume that there's no such path. And to represent there's no such path, we initialize g of v to infinity. Is that okay? So f of v is a little bit interesting because some part of it is g of v. So if you read this sentence here, f of v is the estimation of the length of the shortest path from vertex S, which is our origin, the starting point, through v to x. So the first part is known already because we already know from g of x what is the length of the currently known shortest path from the start vertex to vertex v. That part is kind of known already. We have a specific value. But the rest of it, which is from vertex v to the destination, that part is an estimate. So this is also why you can express f of v as g of v plus h of vx. So let's just kind of pause here a little bit and make sure that this part here, this equation, makes sense to you. The purpose of f of v is an estimate. Okay, it's estimating if we start from the start vertex. go to the vertex B first as a midway point, and then go to the destination. We want to estimate, what is the length of that shortest path. Does that make sense to you? This is how the H value or the heuristic value get into the algorithm. It is part of the estimation. So that explains the initialization. After the initialization, we have one more, which is initializing uppercase O as a set. Uppercase O is doing kind of the same thing as, I cannot remember which letter I used in the previous algorithm. Let me take a look. U, I think. I could be wrong. Q. So uppercase O is kind of doing the job of uppercase Q in Dijkstra's algorithm. Um, this particular set keeps track of vertices that has just gotten its G or H, G of F, G and F values updated. And that's also why we start with the start vertex S, because that is the first one that received a non-infinity value, and that's why we start with it. Is that okay? All right? So you can also kind of say that big O is keeping track of the boundary of expansion, and we start the expansion from the start vertex. That's where we start. And then the rest of this is the control structure. Okay, so the actual complex part of the algorithm starts with this while. Everything else, everything before, is trying to define the given values that we need in order to run the algorithm, and also the initialization of all of the other values, the functions that we need in order for the algorithm to work. All right, so are we still doing okay so far with the algorithm? All right, okay, so let's go ahead and get into the while loop and figure out what it is doing, and you can probably see some similarity between this algorithm and Dijkstra's algorithm, but at the same time, there are also major differences. I think I forgot to mention the pref function. Yep, there we go. There's a pref function here. So let me get back. I do apologize because I forgot. So the pref function is basically a way to backtrack. So by the time we get to the destination vertex, I want to find out how did we get here? In order to find the actual shortest path, this time I'm basically using pref as a previous pointer so I can backtrack. I'm at the destination. Who's my previous vertex? So pref x is going to tell me how I got to the destination. And then once I'm at that particular vertex, I apply pref again. It will tell me who's my previous vertex. So going this way, I can eventually trace my way all the way back to the start vertex. So pref is actually encoding the solution. Is that okay? But the pref of any vertex is undefined at this point. Now, does that make sense to the start vertex? That the start vertex has an undefined previous vertex. That makes perfect sense, right? Because why would I want to know who's previous to the start vertex? This is where I start. So that one legitimately should be undefined. But for the rest of the vertices, well, I haven't even started to explore all the edges yet. So I can't really establish any previous value for all of the other vertices also. So that's why the pref or the previous of all the vertices are initialized to undefined initially. Okay, so that's good. At least I remember to go get back there and talk about that. All right, so this while loop here, the condition of the while loop is different from the condition of the while loop for Dijkstra's algorithm. Dijkstra's algorithm is easy. As long as Q is not empty, we got work to do, right? This one is a little bit more complex, okay? So let's check out what the condition is really trying to specify here. It says right here, if there exists V in big O, this is not a big O of something. The O is basically a set. So I'm basically saying if there is an element in O such that f of b is less than g of x, do the following. Okay, so now we have to kind of remember what f is and what g is. Okay? So f of b is an estimate of the shortest path from the start vertex through v all the way to the destination. That's what f of v is representing. G of x, on the other hand, is the length of the known shortest path from the start vertex, in this case to vertex x. Vertex x is special because it's my destination. Is that okay so far? So what am I really comparing, and why do you think the less than is important in this case? So on one hand, I'm asking, of all of those elements of O, okay, as a set, does any one of these particular vertices has an estimated shortest path that is shorter than the currently known shortest path to the destination? In other words, if this condition fails for every single element in O, there's no hope to find a shorter path anymore. Because, and that portion has to do with the heuristic function cannot overestimate. If we make the assumption that the heuristic function cannot overestimate, that means f of b is a lower bound of the actual length of the shortest path. So if that is already greater than the length of the currently known shortest path to the destination, there's nothing else I can do here. Okay, I cannot possibly find a shorter path at this point. Okay, so I want to make sure that that part makes sense. Are we good so far with that explanation? Okay, all right. All right, so assuming that condition is true, that means there's still a possibility that we can find a shorter path from the start vertex to the destination. Let's go ahead and do some work here. So the work we are doing, the first one is simply to look at, to pick one element out of O as a set, and we'll work with that particular element. The question is, how do we pick? Which one are we supposed to pick? This part here you have seen before when we talked about Dijkstra's algorithm. So if I read this out loud, it says here for all W in O, f of c needs to be less than or equal to f of w. This qualifies this particular element c to be chosen for this iteration of the while loop. So if I do not want to use the mathematical notation, and instead if I want to write a comment for this line of code, what would you have chosen to say is the comment? I mean, I'm asking a really stupid question because the rest of this line explains it. The rest of this line says this picks up the most promising candidate C from the set O. Because again, what are the F values? F of something is the estimated shortest path from the start vertex through vertex W in this case to the destination. So I'm evaluating all the options. I'm saying, okay, let me start up Zerno because I rebooted my computer. So Zerno needs to be restarted. So give me a second here to do that. Oh, wrong screen. Zerno PP, and that is on the wrong screen because I want that to be here. And then we want to start the mirror. And that becomes, it's basically a clone of the same window. The reason why I have to clone the window is because in order to use the tablet and use my stylus, I need Zerno to be running on my actual laptop screen. But since you guys cannot see my laptop screen because I'm recording the other screen, so I have to make a clone so this way you can see it on the projector and it also gets recorded while I can write on the other side. So I just want to explain why it is set up like this. Okay, so this makes it easier to explain because I can actually draw pictures now. So let's say that this is, oh, okay, I forgot to run one more script to get the coordinates correct. So I have to fix the coordinate system of the stylus. There we go. Okay, so let's switch back here. Okay, all right, so let's say this is my start vertex, and this is my destination vertex. Okay, and in between, I got a lot of vertices. So I'm just going to say this is vertex V1, V2, V3, and this is V4. And let's just say that at this moment, the set O has V1, V2, V3, and V4 in it. Okay, so this is representing a scenario of after running the algorithm for a while, we ended up with 4 elements in O. So now the question is, well, out of these 4 vertices, which one am I supposed to pick? And what is F representing in this case? So this part here is known already, okay? I already have a path, okay, from the start vertex to each one of these 4 vertices. So I'm using these kind of crooked lines to represent actual known path. Is it the shortest? Well, maybe, maybe not, okay? Whether it is shortest or not, we know there's a path between vertex S, the starting point, and each one of the V1, V2, V3, and V4 vertices. The rest, I don't know. Okay, this is where we ended. Okay, the early exploration ended with V4. So I have no idea how to connect V4 to X, or to connect from V3 to X, or from V2 to X, or to connect from V1 to X. So what am I supposed to do? This is where the heuristic function comes in handy. In other words, this portion here is G of V1, or it is G of V2. They are representing the length of these crooked line paths. What about these guys? Okay, I'm going to use dotted line here. I suppose I can actually use dotted line, dotted line. Do I want to do that? Draw a line, yeah, but I can change the line style so it's actually dotted, but I'm not going to spend the time to do it. I'm just going to hand draw the dotted lines here. So those are not explored, those are not exact, but I have a heuristic function that can give me some information about those paths. So this one is h of v1 x, this is h of v2 x, h of v3 x, h of v4 x. So if I add g of v1 and h of v1x, now I have f of v1. That's basically what the f function is it really is just combining the g function and the heuristic function to give me an estimate of, well, based on the estimate, what is the length of the shortest path? That's what f is returning. Is that okay? Is this kind of more visual so that you guys can actually visualize and see the relationship between the G, the H, and also the F functions? All right, excellent. But this is also why I want to choose the vertex that has the least F value, because it looks the most promising amongst all the options. Is that okay? All right. Okay. So now we go back to the algorithm, which is here. So basically, I'm still applying the same strategy, which is being optimistic and choose the most promising candidate out of the entire set to consider first. Once I have chosen a particular vertex to quote unquote take a look at, I'm taking it out of O, because otherwise I would have forgotten. Okay, we took a look at this already. Okay, there's no need to keep it in the set. So that's why we have to remove it from the set O. And this part here looks kind of familiar as well, except this time we are not looking at incoming edges. This time we're looking at outgoing edges. So the for each loop, which is down here, is looking at all the neighbors of V, all the neighbors of C that are connected by a single edge, but these are not incoming edges. into C. These are outgoing edges from C. Is that okay? We good so far? All right. So if you look at the graph representation, okay, let me switch back to the graph. Okay. So let's just say that V2 is the one that has the least F value. So what I'm doing now is I'm saying, well, V2 connects to these vertices here. And because I know this path here, going from the start vertex through vertex V2 to the destination is the most promising. So that means one of these two, okay, let's just say that V2 connects to these two vertices here. So that means one of these two is likely to be on the shortest path. Now, is it going to be on the shortest path? Maybe, but based on my strategy of trying to look at the most optimistic choice first, that's what I'm going to explore. Is that okay? So this is why I'm exploring outgoing edges of the most promising candidate out of the entire set of O. Are we still doing okay so far with just kind of intuitively understanding the logic of the algorithm? Okay, all right. So switching back to the description of the algorithm, what do we do? Well, the logic is actually very similar to the one in Dijkstra's algorithm, except the math is a little bit different. So this time we have to look at a temporary variable t, which is the sum of g of c and d of cn. Okay, so getting back to the graph that I was just drawing, this is a little bit easier to explain now. So basically, this is C, okay? Variable C in the algorithm is representing the candidate out of all the options in the set O, that looks the most, optimistic. So if that is C, this is, N, this is also N. It depends on which iteration we are talking about. So for each iteration of the for each loop, I am basically looking at one neighbor of C where it's connected to C by one single edge. Okay? So now what do we do? Well, we already know what is G of C. G of C is the length of the shortest known path up to this point from the start vertex to vertex C. That is G of C. So if I add the distance of Cn to G of C, now I know the length of a path from the start vertex to vertex n. Does that make sense? Now, does that mean it's going to be part of the shortest path from the start vertex, to n? No, it's just it's an alternative. All right, that's what t is representing. So if I switch back to the algorithm, so that's what t is representing. This is the actual length of the shortest known path from vertex s through c to n. Okay, the key part of this sentence is it's going through vertex c. And then we compare t against g of n. So remind me again, what is g of n? It is the length of the shortest known path from the start vertex to vertex n. So this is one option, is to keep the old one that we have discovered before this. And then the alternative is the new path that I'm currently evaluating, which is going from the start vertex first to vertex C, then from vertex C to vertex N. So I'm evaluating these two options. If the new option has a path that has a length that is less than the old option, then I have just discovered a shorter path from the start vertex to vertex N. Is that making any sense? All right. Then what do we do? Okay, we got something new. The first thing is we add the vertex n to the set O. Now there's no such thing as adding an element to a set, not in set notations. So the best way I can do is to put n into a singleton set and then have a union of the set O and the set that only has n as an element, and then use that to update O as a set. Okay, and then what do we do? The next thing we do is we make a recording of, hey, the best way to get to vertex n from the start vertex is to go through C. So the previous vertex of n is vertex C. Okay? And this part is easier to understand if I just kind of switch back to Zernal, because you can now see how vertex n here, its previous is C. So basically, I'm making the assumption that even though I might have discovered the path to n before, but the length of that path is longer than the path starting from vertex S, go through all of this squiggly stuff first to C and then to vertex n. All right? You guys are awfully quiet, which is usually when I start to worry. Okay, so we update the previous, and then we also have to update g of n. G of n is just a value, it's just a number. It is representing the length of the shortest known path from the start vertex to vertex n. Well, I have to update it because I just found a shorter path. So g of n has to reflect the length of the shorter path that I just discovered. All right? And then we have to update the function f also. So f of n is also updated, but it's easy to update that one because f of n is always defined to be g of n plus h of nx. So that one is pretty easy. Are we kind of still doing okay at this point? So the nice thing about keeping track of f, because some people may ask, but why do we keep track of your function f? Because it's so easy to compute it. Because we always know what is g of n, we always know what is h of nx, so why do we want to keep track of f of n? The reason why we want to keep track of f of n is it's just a little bit more efficient when we try to find the minimum of all the f values. I mean, you can do all the recomputation again when you're trying to find the minimum, but this just works out a little bit more intuitively. So we're still doing okay so far with the algorithm. Not so much about the mechanical part, but about the reasoning of why we are doing this. How does it help us find the shortest path? We're still doing okay? All right. So when the while loop is done, okay, so let's go back to the condition of the while loop. So when this condition is no longer true, which basically means for every single vertex in O, f of b is greater than or equal to g of x, which basically translates to, of all the options that you're giving me, every single one is giving me an estimated length of the shortest path going through one of those vertices in O from the start to the destination. Every single one of those options is longer, at least as long as the one path that I have already discovered from the start vertex to the destination. So when that happens, it's like, why would I want to do any more processing? Now, what if you were to change the condition where the cursor is, where the mouse cursor is, and change it so that it becomes while O as a set is non-empty? What if you change that condition? So let me point out where the proposed change is going. So what if you change this condition here to simply say, as long as O, while O is not empty? Would that make the algorithm incorrect? Well, to answer that question, the first thing to ask is, what do you mean by the algorithm being incorrect? Because some people can say, well, if it's doing unnecessary calculation, I call that incorrect. But other people may, such as myself, I would say an algorithm is incorrect if it gives me the wrong answer. Okay, so it's the latter. Okay, so I consider an algorithm incorrect when it gives me the wrong answer. So if I change that condition to say, while O is not empty, do the following, instead of what I already have here, would the algorithm be incorrect? It would not be incorrect. You would be doing something that's meaningless, but it wouldn't find a path that is not the shortest path and call it the shortest path. It would not find the shortest path. It will still find the shortest path. It's just that after it finds the shortest path, you do some extra processing that is useless. That's all. All right? So the final result is if you want to define the solution, I call this a G with a subscript of Sx, which basically means it is a graph, but it represents only one path from the shortest path from the start vertex to the destination vertex. So it becomes, it has the same vertices as G itself, but the set of edges is going to be constructed on the fly such that for all W in V, pref W, excuse me, let me say that one more time. For every W in V, pref W equals to V if and only if VW is in the set of ESX. It's just me reconstructing the shortest path based on the pref function. All right, so that's the algorithm. Let's go ahead and test run it. Okay, we'll find an example and we'll go ahead and test run. All right, so to test run this, I'm gonna have to switch back to Zernal and we'll start a new graph here. So Zernal, new page, after. And we have a definite starting point. We have a definite destination. And then we can have vertices in between, stuff like that. And we'll go ahead and draw some edges first. And just for fun, we're going to have a loop here. And we'll even have a loop here. Because we want to see what happens when we have loops like that in a graph. Would that make the algorithm stop working? We'll find out. And over here, this is vertex S, which is the starting point. This is vertex X, which is the ending point. And this is it, okay? It looks kind of awkward, right? You can see how this vertex here does not actually connect directly to vertex X, and it is part of a loop. So I'm trying to kind of trick the algorithm and say, hey, is that going to work? And okay, just for fun, I'm going to have one over here, and it is a dead end. It doesn't go anywhere. I mean, just for fun, just to see what happens over there. Okay. So now I have to start to assign some distances and also the heuristic function. For this one, I'm not going to try anything too crazy. So we'll go ahead and, well, I take it back. I'm going to try something fun. Okay, so this is, okay, because I'm trying to figure out how to trick the algorithm. Okay, so this is what I usually do, is I'm trying to trick the algorithm. The algorithm says, I'm going to make use of the heuristic function to help me find the shortest path in a reasonable way. I'm going to say, well, let me see if I can give you a heuristic function that defeats the purpose. Okay, it will actually cause the algorithm to explore something that otherwise it would not explore. Okay, but to do that, I have to kind of make sure that the values work out in a certain way. So I'm just going to work out, this is 5, 5, 5, and 5. Okay, and then for the edge going back here, um, I have to make sure that this path here is not any shorter than the 5. So, or we can make it actually shorter. Okay, well, we can do that. No, that won't be very fun. Okay, never mind. We'll make that 7 and the 7 here. We'll make this one even a 3. And then for this loop here, let's make it 0 and 0. Isn't that kind of fun? These edges have a distance of 0, which means, hey, you can loop as many times as you want. It doesn't have any cost to it. So we want to see if the algorithm will go crazy and go like, okay, let's just go around here indefinitely, and it doesn't explore anything else. Okay, we'll check it out. We'll see. We'll find out what the algorithm is going to do. And then for the rest, I just have to make sure these edges do not add up to 5, 5, 5, 5, which is 20. So I have to make these a little bit longer. Let's make the algorithm kind of do the wrong thing. Let's make this 3 and let's make this like 18. Okay? But in addition to just naming the distances of the edges, um, we are also playing with the heuristic values, okay, the h values. So now I have to define the heuristic values from every single vertex to vertex x. Okay, so vertex, okay, now I have to name the vertices. So we have vertex A, B, C, D, E, and F. Okay, so h of the start vertex to the destination vertex. This only has to be an underestimate. So anything that is from 0 up to 20 is okay. This particular heuristic function is not going to be particularly helpful, so we can make it anything. It's not going to change the behavior of running this uh, algorithm too much. So we can just say this is, we can make it exact, like 20, or we can choose anything between 0 and 20. As I said, it doesn't really matter. I'm just going to make it a 5. All right, so h of bx. All right, so how do I want to do this? Oh, we have a first. Excuse me. Let's go in alphabetical order. So we have AX. We can make this one, it doesn't matter because anything within the first edge of the destination, we're going to go there anyway. So it's not going to, it's not going to matter, how we prioritize. It does change how we prioritize, once we uh, get those into the set O. Now it does matter how we prioritize. So let's make this look really good. Okay, this option is going to look very good in the first iteration of the while loop, and then we'll find out it's not actually going to work very well. So HEX is the next one, and we want to make this one looks really good too, so that we find a path to the destination, only to realize later on that that wasn't such a good option. Okay. All right. So we need to work with C now. Okay, vertex C. So we have h of cx. So c is right here, and we have to make sure that the heuristic function is no more than 5 plus 5 plus 5, which is 15. And the question is, do I want to make it exact, which will make it the lowest priority to expand, or not? Yeah, let's make that happen. Let's make this 15. And I forgot one. I forgot bx. So you look at h of bx, and you ask, and you say, b doesn't even have a way to connect to the destination. That is correct, okay? But it doesn't mean that I cannot choose a fun value for the heuristic function. Let's make that 0. Because I think you guys all agree that 0 is less than infinity, right? So that makes 0 a possible option for h of bx. All right, so getting to h of fx, we'll make that exact too, which is 10. And then h of dx, we'll also make that exact, which is 5. So everything along the shortest path, the actual shortest path, is going to look not so good, okay? At least based on heuristic compared to all of the other options. So this is a good way to see what the algorithm will do when we try to misinform it as much as possible. Will it still make the correct decision? Will it still, discover the actual shortest path? And if so, why would it discover the shortest path when we found, when we have all of these other tempting options that are actually totally wrong in terms of, no, that is not part of the shortest path. Are we good so far? Yep.
Isn't the shortest path from S to D to X?
From S to To which one?
D, the bottom one.
From D. You're right. Darn it. Okay. So I have to change this one so that it doesn't look as good. Make it 17. Okay. Yep.
Why are you okay with making those zero? Those
Just to misinform the heuristic, misinform the algorithm, so it will explore things that will lead to a dead end or not the shortest path. Because okay, so one extreme case is to make all the heuristic value zero, in which case it becomes Dijkstra's algorithm, because there's no information. The other extreme is to make the heuristic function or the heuristic value exactly the length of the shortest path. So in which case, it's boring to run the algorithm because every single turn is going to make the right choice and pick out the right element from O. So it won't have actually any chance to have to update anything because the first time you get to a vertex, that is the shortest path already. What I'm trying to do is to misinform the algorithm as much as I can so that it would get to a certain vertex, like in this case, it would get to vertex X, only to find out, that is a path, but it's not the shortest. So we want to kind of trick the algorithm as much as we can. So that's the purpose of putting zeros in some of the heuristic value. It's just me trying to mess with the heuristic algorithm. Okay? So that's a good question. All right. So now we're going to run the algorithm, and I'm not really sure how to do this because there's not enough room on this page to really kind of represent the running of the algorithm. So I got a few ideas. Okay, so let me see if this is gonna work. Um, First of all, we're gonna zoom out here. So zoom out is Control minus as usual. So is that still readable to the people in the back? Still okay? All right, good. And then what I'll do is I'm gonna have to move this window so that way I have space on the other side for a spreadsheet and possibly scroll it up like that so it is actually more, well, actually scrolling it down is better. So this way it is at a corner. Come on, come on. I can't get to the exact location that I want. Okay, let me use the scroll bar instead. There we go. Continuous scrolling works a little better. Okay, so now I can use a spreadsheet to represent the trace because this way I can type, and typing is a little bit faster than handwriting. So I'm just going to use a local spreadsheet for this purpose. And I'm going to have to resize it before I display on the other side because it's way too big. Okay, there we go. And it is still a little bit too big. That's okay. I can resize it like that. Okay, all right. So there are a few things we need to track, when we execute this algorithm. Um, we have the set O, okay, so that's going to take up one column. We have C, which is the chosen vertex to expand from O. We have N, which is the neighbor of C, where Cn is an edge. And then we have T, which is the temporary variable representing the length of the alternate path. And then we have all the G values and all the F values. So we'll start with G first. We have vertices S, what else? A, B, C, D, E, and F, and X. I'm not going to include X here because it's not really needed. So I'm going to stop with F. And we'll make these columns a little bit narrower because otherwise I don't have enough screen space to display everything. Okay, so those are all the G, and now we have all the Fs. Kind of the same deal, the same vertices, like so. And once again, make them a little bit narrower, like that. Okay. T probably can be a little bit narrower too. Oh, I forgot one thing. We also have the pref. Okay, so we have the prefs, kind of the same deal, like so. And with the pref, we actually do need x in the end, and I think with G we also need x in the end. So let me make a few more changes. So this is going to be x. And just to emphasize, all of these columns belong to pref. I'm going to merge all of these cells, and then I'm going to include x also here. So insert column after, like that x, and then merge these cells. And then G, might as well just make item for x, make one item for x here. There we go. Merge all of these, like so. Okay, so I think we're almost good to go. Can I make these two a little bit narrower? And O, the way it is, yeah, we have a little bit more space here. There we go. All right, so now we're gonna initialize everything first, okay? So all the G's except for the start vertex is gonna be infinity. So this is the only one that has a value of 0. Everything else has infinity. Okay, like so. This is the only one that has a value of 0. Everything else is infinity again. And then with pref, everything is undefined, okay? Like so, like that. All right. So I think we got G, F, and pref all initialized. And then O is going to start with a single item in the set, which is our start vertex. So this is row 3. Okay, let me highlight which row here. So row 3 is representing the condition of everything before we start with the while loop. Are we doing okay so far? Okay. So now we're getting into the while loop. The while loop says the first thing we need to do is to say, um, are we ready to exit the loop? Okay. So you guys are going to go, well, obviously we are not ready to exit the loop because we haven't started to do anything yet. But I have to follow the logic of the algorithm to determine whether we are ready to exit the loop or not, which is asking the question of does any element in O, which in this case can only be S, okay, is f of s less than g of x? That's the question that we need to ask. So can someone tell me what is f of s? Actually, I did make one mistake. The f value of s is not 0. It is supposed to be g of s plus h of sx. So I forgot about that. It's supposed to be 5. This is supposed to be 5. Sorry about that. It doesn't really change the outcome of this decision. So is f of s, which is 5, less than g of x, which is infinity right now? Yes? Okay, everybody agree that 5 is less than infinity? Okay, so that means I cannot exit the loop yet, okay, because at least one option represented by elements of O looks kind of promising. Well, turns out that's the only option I have at this point. So the only choice I have is to say, let's choose that one thing in O as a set, and now we have to take it away from O, and now we have to look at all the outgoing edges of S. There are quite a few. There's A, B, C, and D. There are 4 outgoing edges, or 4 neighbors that are connected from vertex S here. If I just kind of follow the order of A, B, C, D, would that be okay? Because it really doesn't matter one way or another. Okay, so let's start with A. So now we are looking at the edge of SA, and then we ask the question. Okay, this is what T is representing. Is what is the length of the path from the start vertex going through vertex S to vertex A? What do you think that's going to be? Well, vertex S has a g value of 0. The edge has a distance of 0 to go to vertex A, which means t is going to be 0. And then we compare t with the g value of A. The g value of A is infinity. I think 0 is less than infinity, right? So that means we have met the condition of the conditional statement. The only if statement, the condition of the if statement is met. Okay, so we have to execute the then branch, which is a whole bunch of operations. The order is not really that important, so I'm just going to go with, let's update g of A to 0, and then we'll go ahead and update f of A as 0 plus h of ax, which is also 0. Okay, well, that makes it look super attractive. And then the pref of A is going to be S. S is going to be the previous, okay, along the quote-unquote shortest path from the perspective of vertex A. And then we have to add vertex A into the set of O. So the set O is now updated to include one element of A. Are we good so far with all of these updates? We good? Okay. And then the next one, oops, okay, I pressed the wrong key. And again. Okay, the next one is vertex B. Okay, so vertex B connects to vertex S with an edge that has a distance of 3. So t is 3. 3 is less than infinity. Okay, so now we get into the then statement of the conditional statement. We get into the conditional statement. So this is 3, and this is going to be 3 plus the heuristic from B to X, which is 0. 3 plus 0 is 3. And then the previous of B is also going to be S over here. And then we also have to remember to add the element, or to add the vertex B into the set of O, like so. And then we have vertex C. The edge from S to C is 5. So that makes the current shortest path from the start vertex to vertex C 5. So we're going to have to go into the then portion of the conditional statement because 5 is less than infinity. So update that. We also have to update, oh, I think I made a mistake here, didn't I? So this is supposed to go here. And then we have 5 plus h of cx, which is 20. And then we say the previous of C is also the start vertex itself. And now we go to vertex D. Vertex D has an edge of 17. So this is 17. Now we say 17 is larger than all of the other values, but nonetheless, it is still less than infinity. So we go into the then portion of the conditional statement, update g of d to be 17. And then we have to update f of d to be, okay, let me look at this part here. So we are looking at f of dx, that's 5, okay, so that's as bad as it can go, which is 22, there we go. And then the previous vertex of D is also going to be vertex S. And now we have to also add, oh, I just forgot to add vertex C to the set. So this is now A, B, C, and this is now A, B, C, D. There we go. Okay. And that concludes the for each loop because we have just explored all of the outgoing edges from the start vertex. A, B, C, D, that's all. Okay. So now we go back to the while loop and ask, are we done yet? Well, let's find out whether we are done yet, okay? In other words, what we want to find is a f value of the elements that are currently in O such that, that f value is less than g of x. Well, that's an easy question to answer because g of x is still infinity, okay? So any known integer or known value is going to be less than infinity. So the answer is, we cannot exit yet. Okay, we still have more iterations to perform. Then the next question is, what should I choose as C? What is the best candidate out of A, B, C, and D? The G values are not useful for that comparison, for that choice. The F values are. So we look at all the F values. F of S is 5, F of A is 0, F of B is 3, F of C is 20, F of D is 22. Well, looks like A is the best option here. Okay, so now we choose vertex A as our candidate. Okay, so we choose A here. And then we have to explore all of the outgoing edges of A. And let me do this before we forget, because we have to remove vertex A from the set O so that we don't get into an infinite loop. Okay. All right, so we look at vertex A. It has two outgoing edges, one going back to vertex S and the other one goes to vertex E. So we'll go to vertex S first, and you go like, isn't the algorithm supposed to have some kind of check to make sure that we are not looping? Well, actually, there is the logic, but it's kind of like hidden. So we go to S here, and then we calculate. Okay, what is G of A? G of A is 0. What is the edge or distance of the edge from A to S? Which is also 0. So T is actually 0 in this case. And then we go to, we compare that to G of A, and we ask, is 0 less than 0? What do you think? Nope, 0 is not less than 0. So that means the condition of the if is false, which also means, well, there's nothing to update now. I did not find a shorter path. Is that okay? This is how we got rid of the infinite loop. Two reasons. One is 0 is not less than 0. We don't even get into the then branch of the conditional statement. But because of that, we also do not add S back into the set. So now it's done. Okay, A is not going to go back to the set, neither is S. So that whole thing about the infinite loop, taken care of, not a problem. So now we move on to the next edge, going from vertex A, it is going to vertex E. So now we have to compute T, which is G of A, which is 0, plus the distance from A to E, which is 3. So this is actually just 3. So we compare the 3 with G of E, which is still infinity. 3 is less than infinity. So now we have a bunch of stuff to update because the condition of the conditional statement is true. We go to the then branch. So this is now a 3, and this is now 3 plus h of ex, which is 0. So this is going to be 3 also. And then the previous of e is going to be a. And then we have to remember to add vertex e to the set. So now we have b, c, d, e in the set. And that concludes the for each loop because we just evaluated all the outgoing edges from the perspective of vertex A. Okay, back to the main while loop. Well, g of x still has not been touched. So it's still infinity, which means we're not done yet. All right, so out of B, C, D, E, and we look at all the H values. So we got B, C, D, E. Which one looks the best? Well, we got a tie here. Whenever you have a tie, because F of B is 3, F of E is also 3. So whenever you have a tie, you go like, either one is fine. Okay, just pick one. Which one do you want me to pick? We are choosing between B and E. Choose B? Okay, let's choose B. So we are choosing B, and we have to remember to take it out of the set. And now, okay, so this is where a spreadsheet is going to be handy because I can use this tool so I can continue to look at the header of each column as I scroll the rest of the same table. Okay. Okay, so now we have to look at all the outgoing edges of B. There's nothing, right? There are no outgoing edges from B, so we're done. The for each loop is an empty loop. There's nothing for me to do. Cool. That's an easy one. Okay, so now we're getting back to the main loop, the while loop, and we're asking, okay, out of the remaining C, D, E, which one looks the most promising? You look at all the F values. C has 20, D has 22, E has 3. Ah, that's an easy one. E is the most optimistic, candidate. Okay, so now we have to remove E from the set. I have to keep reminding myself to do that. And now we have to say, well, look at all the outgoing edges of E. Woohoo! We found our destination. Cool. And then we have to compute T again. So G of E, okay, G of E is 3. 3 plus 18 is 21. So T is 21. We compare 21 to infinity. Okay, so if I scroll down one more cell, we can see that it is still infinity at this point. So 21 is less than infinity. Yeah, that is true. So we got a bunch of stuff to update. This is now 21, and this is also going to be just 21 because h of xx has to be 0 because the shortest path from the destination to the destination has a length of 0, and yet the heuristic cannot overestimate. So that means the h of xx, by definition, has to be 0. All right. The previous thing, yes, so the previous of x is now E, and then we have to add x to the set, C dx. There we go. Are we good so far? So we have just found a path from the start vertex to the destination at this point. So the tricky part is, how do we know that we are not done yet? So now we go back to the condition of the while loop. The while loop says, the while loop asks, I should say, the while loop asks, out of the elements of O, okay, is at least one of these choices having a F value that is less than the G value of X. Now, the G value of X is no longer infinity. It is 21 now. So we are asking, out of the 3 elements here, C, D, X, does one of them have a F value, not G, that is less than 21? Well, C has 20. Well, that's less than 21 already. I think we are not done yet. Okay, so we go into the while loop again. And this time I have to find the smallest because I have to choose the most optimistic candidate. So C has an F value of 20, D is 22, and then X is 21. So we're going to choose C. Okay, so we're going to say, the best candidate is vertex C. Let's take it out of the set. So we have D and X remaining in the set. And now we have to look at all the outgoing edges of C. So the first outgoing edge of C is there's only one, okay? F is the only outgoing neighbor of C. And we look at the G value of C, which is, okay, this is getting a little bit harder to read now because I have to scroll up. So the current G value of C is 5. So we are looking at 5 plus 5, which is 10. And we look at the um, current G value of F. It is infinity. 10 is less than infinity. Okay, we got a bunch of stuff to update. We're going into the then branch of the conditional statement. So this is going to be 10, and this is going to be 10 plus 10, which is 20. And then we have to update, the previous of F is C. And then we have to add the vertex F into the set. So we got dfx now. And that's the only outgoing edge from C, if I am reading this correctly. Yep, it is. So now we have to evaluate, do we have more iterations to go in the while loop? In other words, if I look at vertex D, F, and X, does at least one of these have a lower F value than G of X? G of X is 21. So when we look at the F value, yeah, we got F having a F value, of 20. So F of F is 20. F of D, I cannot remember what it was. So let's look it up. F of D is 22. This is 20, and then f of x is 21. Yep. So we are not done yet. Okay, we cannot exit the loop. So now we have to go into the loop and then ask which one is the most optimistic candidate. So that turns out it is vertex f, and we take f out of the set, so we only have d and x left. And then we have to look at all the outgoing edges of f. There's only one, and it goes to d. We look at g of f. G of f is 10 plus the distance from f to d, which is 5. So we got 15 here. So now we have to look at the 15 and the current g value of d. The current g value of d, if I look it up here, is 17. And then we are asking, is 15 less than 17? The answer is yes. We just found a shorter path to vertex d. So we have to do an update. So f of g of d is now 15. And then we got a bunch of stuff to update too, because f of d would also have to update from 15 to, oh, it used to be, I cannot remember what it was, but um, we have to update it so that it's 15 plus 0. Nope, take it back. I was misreading this. So it's 15 plus 5, which is 20. And then the previous of d is now updated because it used to be vertex s. So now we have to update it to vertex f. And then we have to add vertex d back into the set. Well, it's there already, so there's nothing to do. Are we good so far? Okay. And of course, when we get back to the while loop, the first thing it asks is, are we there yet? The answer is no, because g of x is still 21, and then f of d is 20. Yep, there's still a possible path that is shorter to get to the destination. So this time, we pick D out of the set. Okay, so D is picked out of the set. The set now has the destination itself left in it. And then we have to explore the outgoing edges from D. There's only one, there are two actually. So let's explore the fun one first, which is vertex C, because it kind of forms a loop. And then we look at this and ask, if I go from vertex D to vertex C, what would be the length of that path from, starting from the vertex S? So we have to look up G of D, which is 15, and then we add the distance from vertex D to vertex C, which is 7 to 15. That's 22. Okay, so we have 22 here. And then we ask, well, did we find a shorter path to vertex C? Nope. We got a path of a length of 5 already. So 22, doesn't look attractive at all. So there's nothing to do at this point because the condition of the if statement is false. There's no update. We just go like, yep, nothing we have to do here. So the other outgoing edge from C is going to vertex X, which is our destination. But you can also see in the algorithm, we never really directly compare to the destination and treat it as a special case. It doesn't care, okay? And now we have to compute t, which is f of d, which is 15, plus the distance of the edge from d to x, which is 5. 15 plus 5 is 20. And then we have to ask, well, do we need to update anything? So we are comparing this 20 to 21. We go like, yeah, just by a hair, but it is still smaller. So now we have to go into the then statement of the conditional statement. So we update a bunch of stuff like this one, this one, this one. So we are going from vertex D to vertex X. And we also have to add vertex X back into the set, which is kind of not a big deal because it already has vertex X in it already. So that concludes the for each loop. And now we go back to the while loop. The while loop is asking the same question, are we there yet? And trust me when I say I did not time the lecture today at all. It just kind of works out this way. Nice, right? So when we get back to the beginning of the while loop, it's asking that question again. Do we have at least one element in O such that f of that particular element is less than g of x? Well, what is g of x? We just updated it. It's 20 now. What is f of x? We only got one element left in O, and f of x is also 20. 20 is less than 20 is false. So there are no more promising paths ever in this entire thing. We're done. We get out of the loop. So once we get out of the loop, okay, this part is going to be really kind of quick, is we use the previous to backtrack. So we start with the destination vertex. The destination vertex says, okay, my previous vertex is vertex D. Vertex D says my previous vertex is vertex F. Vertex F says my previous one is C. And then C says its previous one is S. Done. That's the shortest path. Is that okay? So even though I really kind of try my best to fool the A star algorithm, it's okay. It found the shortest path anyway. So is that okay? All right. So I will give you assignments, over the weekend, on these algorithms. You're gonna have to do a trace similar to what I just did in class, and you can use a spreadsheet. So there's no need to handwrite everything with a ruler and stuff like that. Just use a spreadsheet. The Google Sheets work really well, and that's going to be your homework assignment over the weekend. Because I think until you actually do it yourself, like try it out a few times, you can say, I kind of understand what you said, but until you actually do it, the connection is not solid in your mind. Okay, so that's what I will give you guys, over the weekend, as an assignment. All right. All right. I'll see all of you next Monday. Have a nice weekend.
Last weekend.
Mm-hmm. Well, I do meet with you virtually on Friday. Yep. And also Anthony, who has left already.
Do you plan to upload your